Welcome to the peaceful space of sleep-friendly science, where we journey into the quiet and elegant architecture of mathematics to explore a profound mystery. Is it an invention of our minds, or the native language of the universe? Tonight, we are not solving equations. We are listening to them. We are asking whether the universe whispers its secrets in a code of numbers, a code we are only just beginning to decipher. Let your mind become still, and let's explore this beautiful puzzle together. Now settle in, take a deep breath, and let the soft sounds guide you as we begin tonight's journey into the unknown. Section 1. The Ghost in the Machine. As you rest here, feel the world around you. The gentle pressure of the blankets, the soft support of the surface beneath you, the quiet rhythm of your own breathing. This is the physical world, the world of matter and sensation, a world that feels solid, real, and immediate. But tonight, our journey takes us into a different kind of reality, a realm that is weightless, colorless, and soundless. It is the world of pure thought, the silent, invisible kingdom of mathematics. And our story begins with a strange and wondrous connection between these two worlds. It begins with what one physicist called the unreasonable effectiveness of mathematics, a mystery so profound it feels like magic. Imagine, for a moment, the mind of Isaac Newton in the 17th century. He sits not in a modern laboratory, but in quiet contemplation, armed with little more than paper, ink, and the power of his own reason. He is wrestling with the profound question: what is the force that holds the moon in its steady, graceful orbit around the Earth? And is it the same force that causes an apple to fall from a tree to the ground? He does not build a rocket to travel to the moon. He does not possess a supercomputer to model the cosmos. He does one of the most powerful things a human being can do. He thinks. And in the quiet sanctuary of his mind, he formulates an idea, an abstract relationship between mass, distance, and force. He then translates this thought into a simple, elegant line of symbols. F equals G mm2 / R superscript 2. This was not a singular event. The story repeats itself throughout history, becoming more and more uncanny. A century and a half after Newton, the Scottish scientist James Clerk Maxwell was contemplating the disparate phenomena of electricity and magnetism. He wrote down a set of 4 beautiful, symmetrical equations, another masterpiece of abstract thought. But when he examined his own creation, the equations themselves seemed to whisper a secret to him. They predicted that a certain kind of wave should exist, an electromagnetic wave that would travel at the speed of light. The mathematics on the page insisted that such a thing must be real. Decades later, Heinrich Hertz generated and detected these very waves in his laboratory, the radio waves that now carry our voices and stories through the air. The ghost in the machine had not just described the world as it was. It had predicted a part of the world no one had yet seen. The mystery deepens as we journey into the bizarre and counterintuitive world of the atom. In the early 20th century, physicists were faced with a reality that defied all common sense. A world of particles that could be in multiple places at once. A world governed by probability and uncertainty. Once again, it was mathematics that provided the key. Erwin Schrödinger wrote down an equation, a purely abstract mathematical statement, that described the behavior of a quantum wave function. And again, against all odds, this abstract piece of mathematics perfectly described the weird, shimmering, probabilistic reality of the subatomic realm. This is the unreasonable effectiveness. There is no logical reason why the universe should be comprehensible to us. There is no law that states that the fundamental workings of reality must be expressible in elegant, concise mathematical formulae that a human mind can discover and understand. And yet they are. It is as if we are living inside a grand, cosmic puzzle, and we have discovered that a language we invented in our own heads is the exact language in which the puzzle's solution is written. So we are left with a profound and beautiful question. Is mathematics merely a human invention, a clever and useful language we created to describe the patterns we see around us, like a well-crafted key that just happens to fit the lock? Or is something deeper going on? Is the universe itself inherently mathematical? Is the ghost of number and form not something we impose upon the machine, but the very logic upon which the machine was built? Is mathematics not a key we made, but a discovery of the shape of the lock itself? Section 2. The mind's beautiful game. This uncanny resonance between the world of pure thought and the world of physical things is a profound mystery. So, let us explore one of the two great possibilities, the one that is perhaps more intuitive and grounded. Let us consider that mathematics is not a universal truth we are uncovering, but rather a purely human creation, a magnificent and intricate game invented by us for us. Imagine, if you will, the game of chess. It is a world unto itself, governed by a small set of simple arbitrary rules. A pawn moves forward one space, a knight in the shape of an L, a bishop diagonally. These are the starting assumptions, the axioms of the game. There is no deep, cosmic reason why a knight must move this way. We simply decided that it should. We invented the rule. And yet, from these few simple invented rules, a universe of breathtaking complexity emerges. An almost infinite number of possible games can be played. We discover deep strategies, elegant opening moves, beautiful and surprising checkmates. We can write entire libraries of books exploring the consequences of these simple rules. The game of chess is a system of perfect internal logic. It is a cathedral of pure reason, built upon a foundation of our own making. This is the argument for mathematics as a human invention. In this view, mathematics begins not with a discovery but with an agreement. We start with a few foundational agreements which we call axioms. An axiom like parallel lines will never meet, or a number added to its negative equals 0. We do not find these truths written in the stars. We propose them as the fundamental rules of our game. They are the starting positions of our logical pieces on the board. And once these rules are agreed upon, the game begins. The rest of mathematics, all of its vast and towering theorems, its strange and beautiful proofs, are simply the logical consequences of playing this game. A mathematician is not an explorer charting an unknown continent. They are a grandmaster of chess, exploring the deepest, most subtle implications of the rules we created at the beginning. The beauty we find in a perfect mathematical proof is the same beauty we find in a brilliant, unexpected chess combination, a thrill of seeing the hidden potential within the rules we ourselves set in motion. But this raises the great question from our first chapter. If mathematics is just a game we invented, why is it so unreasonably effective at describing the universe? Why does the real world seem to obey the rules of our mental game? The answer, from this perspective, lies not in the universe but in our own minds. Our brains did not evolve in a vacuum. They evolved within this universe, and their primary job was to ensure our survival. A brain that is good at perceiving patterns, at noticing the cyclical rhythm of the seasons, at distinguishing one wolf from 3 wolves, at predicting the arc of a thrown spears, a brain that is more likely to survive and pass on its genes. Our minds are, at their very core, pattern recognition machines. Mathematics, in this view, is the ultimate refinement of this innate ability. It is the language we invented to make our pattern recognition precise. We took our fuzzy, intuitive sense of more and less and formalized it into the rigorous system of numbers. We took our perception of shapes and formalized it into the logical world of geometry. We built the game of mathematics, but we built it to mirror the patterns we were already wired to perceive in the world around us. Think of it like this. Imagine a master artisan who, after studying the flow of water in a river for years, decides to build a net to catch fish. The artisan invents the concept of the net, the pattern of knots, the shape of the weave. The net is a human creation, but it is designed with the river in mind. When the artisan casts the net into the water and it perfectly catches the fish, it is not a miracle. It is a testament to how well the artisan understood the patterns of the river, and how skillfully they designed their invention to match them. So it is with mathematics. We are the artisans. Our minds have studied the patterns of the universe, and we have woven a beautiful logical net of mathematics. When we cast this net into the cosmos and find that it perfectly describes the orbit of a planet or the behavior of a particle, we should not be unreasonably surprised. We are simply admiring the effectiveness of our own invention, a tool we built for this very purpose. The universe isn't speaking mathematics. We are speaking mathematics at the universe. And we are delighted when our invented language proves to be a powerful and poetic way to tell its story. The ghost in the machine, from this perspective, is the ghost of our own logic, a beautiful reflection of the pattern-seeking mind that created it. Section 3: Echoes of a Platonic Realm. We have explored the beautiful and compelling idea that mathematics is a human invention, a sublime game of logic we created to make sense of the world. It is a comforting and grounded perspective. But now let us be brave and let us wander down the other path. Let us entertain a far stranger, more mystical, and for many mathematicians, a more deeply felt possibility, that mathematics is not an invention at all, but a discovery. This is an ancient idea, most famously associated with the Greek philosopher Plato. To journey into this way of thinking, you must first imagine that our physical world, the world of trees and stones, of our own bodies, is not the only reality. Plato believed that there exists another realm, a perfect, timeless, and unchanging world of pure forms and ideas. This is a world that cannot be touched or seen, but can only be perceived, however faintly, by the human mind through the faculty of reason. In this Platonic realm, there exists the perfect form of a circle, not a drawing of a circle, which will always be imperfect, but the very essence of circleness itself. There exists the perfect form of justice, of beauty, and of truth. And, most importantly for our story, there exists the universe of mathematical objects. The number 2 exists here, not as a symbol on a page, but as the pure eternal concept of two-ness. The axioms of geometry are not human agreements. They are fundamental laws of this abstract reality. And all the theorems and proofs that follow from them are not inventions, but pre-existing truths, timeless relationships between these forms, waiting patiently in this silent realm to be discovered by a human mind. From this perspective, a mathematician is not a creator but an explorer. They are like an astronomer peering through a telescope into the night sky, charting constellations that were there long before the telescope was ever built. The mind of the mathematician is the telescope. It is a special kind of lens, one that can, on rare and beautiful occasions, focus on this abstract, non-physical reality and bring back a report of what it has seen. When a mathematician shouts "Eureka!", it is not the cry of a successful inventor, but the gasp of a discoverer who has just glimpsed a new and stunning feature of this hidden landscape. This view changes everything. It explains the unreasonable effectiveness of mathematics in a completely different way. The reason mathematics so perfectly describes the physical universe is, in this view, simple. The physical universe itself is a shadow, an imperfect copy, of this deeper mathematical reality. The universe doesn't just happen to obey mathematical laws. The universe is built upon them. The mathematical truths exist first, in this Platonic realm, and the physical world is then molded and constrained by these eternal principles. The orbit of a planet is not just described by an equation. The equation is the reason for the orbit. The mathematical form of an ellipse exists in this abstract realm, and the planet, in its physical reality, has no choice but to follow this pre-existing path. The ghost in the machine is not the ghost of our own minds. It is the ghost of this perfect mathematical blueprint. The machine of the universe is just the physical manifestation of this ghostly architecture. This idea can feel deeply unsettling. It suggests that a part of reality is completely inaccessible to our senses, a realm of pure, cold, eternal truth that exists independently of humanity, of life, of the entire physical cosmos. It would mean that the truths of mathematics were there before the Big Bang, and they will still be there after the last star has faded to black. And yet, this is precisely how many of the world's greatest mathematicians have described their own experience. They do not feel like they are inventing. They speak of a feeling of discovery, of stumbling upon truths that feel more real, more perfect than anything in our messy physical world. They feel that they are merely pulling back a curtain on a pre-existing reality, a reality of sublime and perfect order. They are listening to the echoes from this Platonic realm. Does this realm truly exist? Or is it simply a powerful and compelling metaphor for the objective and universal nature of mathematical truth? We cannot know. We cannot send a probe to the world of forms. But to contemplate it is to open ourselves to a sense of profound wonder. It suggests that our minds, the soft biological machinery in our skulls, have a mysterious connection to something timeless and transcendent. It suggests that when we do mathematics, we are not just playing a game, we are engaging in a dialogue with the very structure of existence. Section 4. The Secret of the Circle. We have contemplated the strange and beautiful possibility of a Platonic realm, a silent, timeless world of perfect mathematical forms. It is a grand and abstract idea, so let us now make it concrete. Let us take a single perfect object from that realm and hold it gently in our minds. Let us consider the circle. Imagine right now a perfect circle, not one drawn on paper, which will always have a slight tremor from the human hand. Not one rendered on a screen which is made of finite pixels. Imagine the pure idea of a circle. Its definition is one of sublime simplicity. It is the set of all points in a plane that are at a fixed distance from a single central point. That is its soul, its genetic code. It is a shape of perfect democratic equality, where every point on its edge is equally important. This perfect idea of a circle has a secret it is willing to share. A property that is woven into its very being. It has a circumference, the distance you would travel if you were to walk along its graceful, curving edge. And it has a diameter, the straight line that passes directly through its center, connecting two opposite points. For millennia, human beings have noticed a remarkable relationship between these two measures. If you take the circumference of any circle and you divide it by its diameter, you always get the same number. It does not matter what circle you choose. It could be the tiny shimmering circle of a dewdrop on a blade of grass. It could be the circle of a wedding ring on a finger. It could be the vast, nearly perfect circle of the sun as it appears in our sky, or the unimaginable circle traced by the event horizon of a black hole. In every case, the ratio is the same. It is a cosmic constant. We have given it a name, a simple letter from the Greek alphabet, pi or pi. Here, in this simple universal number, we find one of the most powerful arguments for mathematics as a discovery, not an invention. If mathematics were just a human game, a set of rules we created, we might expect it to be neat and tidy. We might expect our most fundamental shapes to be described by simple, elegant numbers. But pi is anything but tidy. Try to write pi down. We begin with 3.14159 and we continue. We have now used supercomputers to calculate the digits of pi into the trillions, and we have found that they never, ever end. And more than that, they never fall into a repeating pattern. The digits march on into infinity in a sequence that appears, for all intents and purposes, to be completely random. This number, so simple in its definition, the ratio of a circle's circumference to its diameter, is infinitely complex in its expression. It is what we call an irrational and even a transcendental number. This is a profound clue. Did we invent this infinite, chaotic river of digits? Or did we simply stumble upon it? When we decided to investigate the perfect form of the circle, did we create this endless number? Or did we simply listen to the secret the circle whispered to us? Feels like the latter. It feels as though the property of pi is an inherent, unchangeable, and somewhat stubborn fact about the nature of reality. We did not choose for pi to be irrational. We discovered, to our astonishment, that it was. The case grows stronger when we consider the universality of this truth. If we were to one day meet an intelligent civilization from a distant galaxy, A civilization with a completely different biology, culture, and history. They would not share our art, our music, or our languages. But if they have investigated the nature of a circle, they will have discovered the exact same number. Their symbol for it will be different, but its infinite, non-repeating sequence of digits will be identical. How can this be, if mathematics is purely a product of the human mind? The universality of pi suggests that it is not a feature of human psychology, but a feature of the universe itself, accessible to any mind capable of reason. The mystery of pi becomes even deeper when we find it showing up in places that have nothing to do with circles. If you drop a set of needles randomly onto a lined piece of paper, the probability that a needle will cross a line is governed by pi. If you listen to the gentle swing of a grandfather clock, the equation describing its period involves pi. Pi appears in the mathematics of waves, in the distribution of prime numbers, and in the Heisenberg uncertainty principle that governs the quantum world. Why? Why does this one number, the secret of the circle, appear as a fundamental constant woven through so many different aspects of reality? It is as if we have found a single golden thread, and as we follow it, we find it is part of the warp and weft of the entire cosmic tapestry. Pi stands as a silent witness. It does not feel like an invention. It feels like a discovery of a truth that is far older, far grander, and far more mysterious than the human mind that was lucky enough to find it. It feels like an echo from that Platonic realm, a timeless fact of existence. Section 5. Nature's Favorite Numbers. We have listened to the transcendent secret of the circle, the endless universal song of pi. It whispers to us of a mathematics that seems to be discovered, not invented. But perhaps that is a special case, a feature of pure abstract geometry. Let us now turn our gaze from the perfect Platonic world of ideas to the messy, tangible, and living world around us. Let us look for numbers not in the sky but in the soil. For here too, in the realm of biology, we find that nature seems to have a strange and persistent preference for a certain set of numbers. Our story begins not with a Greek philosopher, but with a 13th century Italian mathematician named Leonardo of Pisa, whom we know today as Fibonacci. He was not contemplating the cosmos. He was pondering a rather whimsical, practical problem about the breeding of rabbits. He imagined a single pair of rabbits in a field. How many pairs of rabbits would there be after a year? He wondered if each pair produces a new pair every month, and each new pair becomes productive after 1 month. As he worked through this simple, idealized puzzle, a curious sequence of numbers emerged. In the first month you have 1 pair. In the second, still 1. In the third, the original pair has a new one, so you have 2. In the fourth month, the original pair has another, and the first offspring is now mature enough to have its own, so you have 3. Then 5. Then 8. Then 13. A pattern revealed itself. Each number in the sequence was simply the sum of the 2 numbers that came before it. 1 1 2 3 5 8 13 21 34. And so on forever. This is the Fibonacci sequence. At first, it seems like a charming mathematical curiosity, the answer to a quaint puzzle. It is a simple man-made game, born from a thought experiment about rabbits. An invention. But this is where the mystery begins. Because when we put down the pen and paper and go outside into the natural world, we begin to find these very numbers, these Fibonacci numbers, showing up everywhere with an almost spooky insistence. Look at a flower. Count the petals. A lily has 3 petals. A buttercup has 5. A delphinium often has 8. Marigolds can have 13, asters 21. A daisy usually has 34 or 55. It is not always perfect, but nature shows a stunning and overwhelming preference for Fibonacci numbers. Why? Why would the genetics of a plant care about the solution to an Italian's rabbit puzzle? The pattern continues. Look at the head of a sunflower. The tiny seeds are not arranged randomly. They form a mesmerizing pattern of interlocking spirals. Count the spirals curving to the left, and then count the spirals curving to the right. you will almost always find a pair of consecutive Fibonacci numbers, 34 and 55, 55 and 89, or even 89 and 144. Look at the scales on a pine cone, or the bumps on a pineapple, or the branching of a tree. The same spirals, the same numbers emerge again and again. This is not a coincidence. It is a matter of profound efficiency. For a plant, the arrangement of its leaves, petals, or seeds is a critical problem of survival. It needs to arrange them in a way that maximizes their exposure to sunlight and rain, and packs them in the most compact way possible. It turns out that the most efficient way to do this, the perfect solution to this engineering problem, is to grow a new part, a new leaf or seed at a specific angle of rotation relative to the last one. That angle is approximately 137.5 degrees. And what is so special about that angle? It is intimately related to the Fibonacci sequence. More specifically, it is connected to a number that this sequence points towards. If you take any two consecutive numbers in the Fibonacci sequence and divide the larger one by the smaller one, 8 divided by 5, 13 divided by 8, 21 by 13, you will notice that the result gets closer and closer to a specific irrational number. That number is approximately 1.618, and it is known as the golden ratio, or phi. That perfect angle of 137.5 degrees is what you get when you divide a full circle by this golden ratio. It seems that life, through the long, slow, unthinking process of evolution, has stumbled upon this mathematical secret. A plant doesn't know mathematics. It doesn't solve equations. But the plant whose genetic code happens to produce this optimal angle of growth is the one that thrives. Its descendants inherit this trait. Over millions of years, life has converged on this perfect mathematical solution. So, what does this tell us in our great debate? The Fibonacci sequence was invented as a game. The golden ratio is a pure, abstract mathematical concept. And yet, they are also discovered by life itself as the optimal solution to real-world problems of packing and growth. It suggests a beautiful synthesis of our two viewpoints. The mathematical truths may exist independently, as a landscape of possibilities and optimal solutions. And life through evolution and we through conscious thought are both explorers of this same landscape. We are both, in our own way, discovering nature's favorite numbers, uncovering a deep mathematical logic that is woven into the very fabric of being. Section 6. Reality of imaginary numbers. We have found numbers hiding in the petals of a flower, and heard them in the whisper of a circle's circumference. These examples, compelling as they are, still have a link to the physical world we can perceive. But now our journey must take a turn into a realm so abstract, so seemingly disconnected from reality, that it feels like a pure invention of the human mind. Let us explore the strange and beautiful story of a number that shouldn't exist. Imagine the number line as you learned it in school. It is a straight, infinite road. In the middle is the tranquil country of 0. To the right, the road stretches on through all the positive numbers, towards an infinite horizon. To the left, it stretches through all the negative numbers into an opposite infinity. This road is logical, predictable, and for a long time it seemed to be the entire world of numbers. On this road we can perform simple operations. Addition is walking forward. Subtraction is walking backward. Multiplication is a form of repeated walking. And a special kind of multiplication exists. Multiplying a number by itself or squaring it. If you take a positive number, say 2, and multiply it by itself, you get a positive number 4. You move further down the positive road. If you take a negative number, say -2, and multiply it by itself, the two negatives cancel out, and you still get a positive number 4. This seemed to be a fundamental law of the road. Any number, when multiplied by itself, must land on the positive side of 0. And so, for centuries, a certain question was considered nonsensical, a logical impossibility. What is the square root of a negative number? What number, when multiplied by itself, gives a negative result like -1? There was no answer on the straight, familiar road of the number line. The question led to a place that didn't exist. It was a mathematical dead end. Then, in the 16th century, a handful of bold and playful mathematicians did something remarkable. They didn't find an answer. They created one. They said, in essence, let us pretend. Let's imagine a number whose special property is that when you multiply it by itself, you get -1. We know it's not real, so let's give it a name to reflect that. Let's call it imaginary. And they gave this ghostly number a symbol, I. This was a profound act of intellectual rebellion. It was like a writer introducing a mythical beast into a work of historical nonfiction. At first, I was treated as a mere trick, a clever but ultimately nonsensical tool for solving certain kinds of equations. It was a piece of mathematical scaffolding you could use in your intermediate steps, as long as you made sure it vanished from the final real answer. But then, mathematicians discovered something beautiful. They realized that I was not just a random invention. It had a deep and elegant geometric meaning. If multiplying a number by -1 is like turning 180 degrees on the number line, turning from 1 to -1, then multiplying by I must be the square root of that turn. And what is the square root of a 180-degree turn? It is a 90-degree turn. Suddenly the ghost had a home. I was not on the infinite road of the number line at all. It was a single step taken at a perfect right angle to that road, into a new hidden dimension. This opened up a vast and beautiful new landscape. The complex plane. A two-dimensional world where any number could be described by how far it was along the real road, and how far it was along this new imaginary direction. It was a world of rotations, of spirals, of waves. For 2 centuries this remained its home. A beautiful, self-consistent, and wonderfully useful mathematical game, but a game nonetheless. And then came the 20th century, and quantum mechanics. As physicists like Erwin Schrödinger and Paul Dirac tried to write the equations that govern the fundamental reality of the universe, the world of electrons, photons, and the very fabric of matter, they found themselves confronted with an astonishing fact. The imaginary number, I was already there, waiting for them. The Schrödinger equation, which describes how a quantum system evolves over time, is not an optional extra. It is one of the foundational pillars of modern physics. And right there, nestled in its core, is the imaginary number I. And unlike the earlier engineering equations, it does not just cancel out at the end. It is a non-negotiable part of the description of reality. It is woven into the very evolution of the quantum wave function. If you try to remove I from the equation, it simply no longer describes the world we live in. This is perhaps the most stunning and unreasonable moment in our entire story. A number that was born from a playful act of pure imagination, a concept so divorced from reality that we branded it imaginary, turns out to be a fundamental component of the universe's source code. It's as if a poet wrote a verse about a unicorn, only for biologists to discover that the creature's DNA was essential for all life on Earth. How can this be? How can a human fiction, a ghost we invented, be an essential gear in the machine of the cosmos? This profound discovery pushes us away from the idea of mathematics as a mere human game. It suggests that the complex plane was never just a mental landscape. It was a map of a territory that truly exists. And the number I was never imaginary at all. It was a discovery of a hidden dimension of reality, one our minds were not yet ready to see. Section 7. The universe's native tongue. We have seen the ghost of an imaginary number become a cornerstone of reality. This strange and beautiful truth hints that the universe might not just be described by mathematics, but that it might be, in some profound sense, made of it. Our journey now brings us to the feet of a man who took this idea to its ultimate conclusion, a man who believed so deeply in the power of abstract mathematical reasoning that he used it to rewrite our understanding of space, time, and the very force that holds us to the Earth. This is the story of Albert Einstein and his search for a new theory of gravity. For over 2 centuries, Newton's law of gravitation had reigned supreme. It was a masterpiece of science, a simple and elegant equation that worked with stunning precision. It described the fall of an apple and the orbit of the moon. It was a powerful tool. But to Einstein, it was not a satisfying explanation. Newton's theory described how gravity worked, but it didn't say why. It posited a mysterious, invisible force that acted instantaneously across the vast, empty distances of space. A spooky action at a distance that Einstein found deeply unsettling. So, in the early 20th century, Einstein set out not just to refine Newton's theory, but to replace it entirely. And his approach was revolutionary. He did not begin with new experiments or new physical observations. He began with a thought. A simple, beautiful thought experiment. He called it his happiest thought. He imagined a man falling from the roof of a house. As this man falls, he feels no gravity. He is weightless. An object he lets go of from his hand will float beside him. In this moment of freefall, the force of gravity has vanished. From this simple imagined scenario, a profound insight emerged. Gravity and acceleration are, in some deep sense, equivalent. They are two sides of the same coin. This was the seed of his new theory. But to make this seed grow, to turn this beautiful physical insight into a rigorous predictive science, he needed a language. And the language of everyday physics was not enough. The mathematics of his time was built for a world of flat, unchanging space and a steady universal time. It was the language of Euclid. But Einstein's insight suggested that gravity was not a force in space, but a feature of space. It was a curvature, a warp in the very fabric of reality. He needed a new language to describe a curved and dynamic universe. And so, he turned to the world of pure mathematics, a world that was, to him, a source of creative inspiration. He began a long and arduous journey, guided by his friend Marcel Grossman, into a strange and esoteric branch of geometry that had been developed decades earlier by the mathematician Bernhard Riemann. Riemann had not been thinking about gravity or the physical world at all. Like a true mathematical purist, he had been playing a beautiful abstract game. He asked, what are the mathematical laws that would govern any kind of curved space, in any number of dimensions? He had created a whole new grammar, a set of tools and equations. The mathematics of tensors and manifolds describe these imaginary, curved worlds. At the time, it was seen as a work of pure, unadulterated mathematical art, with no conceivable practical application. It was a solution waiting for a problem. Einstein had found the problem. For years, he struggled to learn this difficult and abstract mathematical language, to translate his physical intuition about gravity into Riemann's precise geometric framework. He described it as a battle, a desperate search in the dark. He knew the physical principle had to be right, and he had a deep faith that this abstract mathematics held the key. He was trying to find the one specific equation, hidden in the vast landscape of Riemann's possible geometries, that would correctly describe our universe. Finally, in 1915, he found it. The Einstein field equations. It is an equation of breathtaking elegance and power, a single line of tensor calculus that stands as one of the crowning achievements of human thought. And what does it say? It says that matter and energy tell spacetime how to curve, and the curvature of spacetime tells matter how to move. It is a complete reimagining of reality. Gravity is not a force. The Earth is not pulling you down. The Earth, by its very mass, is creating a deep, invisible valley in the fabric of spacetime around it. You and the chair you are in and the floor of the room are simply resting at the bottom of this gentle cosmic dimple. The moon is not being pulled by the Earth. It is trapped in the Earth's spacetime valley, endlessly rolling around the edge like a marble in a great invisible bowl. And the proof of this astonishing vision? The mathematics itself made predictions. It predicted that the light from distant stars should bend as it passes by. The sooner prediction confirmed during a solar eclipse in 1919, making Einstein a global celebrity. It predicted that time itself should run slower in a strong gravitational field, a bizarre effect that is now a crucial daily correction in our GPS systems. This beautiful, abstract mathematics, born from the playful mind of a 19th-century mathematician, had become the universe's native tongue. Einstein hadn't just used math to describe the universe. He had listened to the universe, and he had heard it speaking the language of Riemannian geometry. Section 8. A blueprint in the brain. We have stood in awe before the power of a purely abstract language to command the cosmos. We have heard the universe speak in the tongue of Riemannian geometry, and we have seen Einstein listen and understand. This conversation between mind and reality is so profound, so perfect, that it leads us to wonder if mathematics is not a human invention, but a fundamental truth of existence. But this raises an equally deep and wondrous question. How is it that we can understand this language? How did the soft, wet, biological machine of the human brain, a thing of flesh and electricity, become fluent in the language of the stars? Let us for a moment gently pivot our perspective. Let us turn the telescope around, away from the distant Platonic realm, and point it back at ourselves, at the intricate, evolved architecture of our own minds. Perhaps the secret of mathematics' power lies not in the stars, but within our skulls. This is the evolutionary view, the idea that our brains are not blank slates upon which we write mathematics, but are themselves pre-inscribed with a mathematical blueprint. Journey back with me, not to the dawn of the universe, but to the dawn of our own humanity. Imagine an early ancestor on the vast, open savanna. This ancestor is not a physicist or a mathematician. They are a creature struggling for survival in a world of immediate dangers and opportunities. And in this struggle, certain cognitive skills are not a luxury. They are a necessity. First, there is the whisper of number. Our ancestor needs to know with a primal intuitive certainty the difference between one approaching predator and a pack of 3. They need to glance at a bush and instantly assess whether it holds enough berries to be worth the effort of gathering. This is not formal counting. This is a deeper, more ancient faculty, a subconscious sense of how many, an ability that we see even in crows, in lions, and in human infants. This is the raw, unrefined ore of arithmetic, a cognitive template for quantity etched into the brain by the relentless pressure of survival. Then there is the instinct for space. To hunt successfully, our ancestor must be able to predict the graceful parabolic arc of a thrown spear. To navigate their territory, they must be able to mentally map the shortest path between a safe cave and a source of fresh water. To build a simple shelter, they must have an intuitive feel for angles, for stability, for shape. This is not the rigorous world of Euclidean proofs, but it is the raw material of geometry, a deep, intuitive physics of the everyday world, hardwired into the neural pathways that process vision and motion. And underlying it all is the grammar of consequence, the quiet hum of logic. If the clouds gather in this way, then the rain will come. If I leave these tracks, then a predator can follow me. This fundamental structure of if-then reasoning is the very engine of survival. And it is also the very soul of mathematical proof. It is the ability to link cause and effect, to follow a chain of deductions from a premise to a conclusion. From this evolutionary perspective, we are born mathematical. The blueprint is already there. Natural selection, acting as the silent, patient architect over millions of years, has designed a brain that is predisposed to see the world in a mathematical way, because a mathematical perception of the world is a successful one. We do not invent the idea of quantity or space or logic. We are born with these concepts sketched into our very being. So what, then, is formal mathematics? It is the glorious symphony we have built from these ancient folk song melodies. We took our innate fuzzy sense of more and less, and refined it into the precise, powerful system of arithmetic and number theory. We took our intuitive grasp of shapes and paths and formalized it into the magnificent, logical cathedral of geometry. We took our simple, if-then survival instinct and elevated it into the art of rigorous deductive proof. Mathematics, in this view, is a human creation, yes, but it is not an arbitrary one. It is the systematic and cultural refinement of the cognitive tools that evolution gifted us. This also offers a stunning explanation for the unreasonable effectiveness that baffled us earlier. Why can our mathematics, forged on the savannah to dodge predators, describe the esoteric world of quantum mechanics? Think of your own hands. They evolved for the specific, practical purposes of grasping a branch, of chipping a tool from stone. And yet, with those same hands, a human being can play a Chopin piano concerto, or perform delicate neurosurgery. The hand possesses a power and a flexibility that transcends its original evolutionary purpose. So it may be with our minds. Our mathematical blueprint was laid down for simple terrestrial survival. But the tools it gave us, the capacity for abstraction, for rigorous logic, for pattern recognition on the deepest levels, are so powerful, so fundamental, that they have an unreasonable effectiveness of their own. We have taken the tools meant for counting lions and have pointed them at the heart of the atom, and to our astonishment they still work. The blueprint, it turns out, was for a far grander machine than we ever could have imagined. We have discovered a power within ourselves that we did not know we had, a power etched there by the patient hand of evolution. Section 9. The Edge of Reason. We have journeyed through a universe that seems to be written in the language of mathematics, and we have explored the possibility that our own minds were forged by evolution to understand this very language. It is a story of beautiful, almost perfect harmony between the inner world of human thought and the outer world of cosmic law. Can feel as though, with enough time and enough thought, we might one day understand everything. That we might, in the end, create a theory of everything, a single all-encompassing mathematical framework that explains all the forces of nature, a final and complete chapter in the book of the universe. But our journey must now take us to a place of profound and beautiful humility. We must visit a quiet office in the Vienna of the 1930s, where a brilliant and reclusive young logician named Kurt Gödel made a discovery so deep and so shattering that it placed a fundamental and eternal limit on what mathematics can ever hope to achieve. He discovered that the dream of a complete and final theory is, and always will be, just a dream. He took us to the very edge of reason, and showed us that there are truths that lie beyond its reach. To understand Gödel's discovery, we must first understand the great ambition of mathematicians at the turn of the 20th century. They sought to place all of mathematics on a perfectly solid logical foundation. Their dream was to create a formal system, a set of axioms and rules of inference, that was both complete and consistent. Consistent means that the system would never contradict itself. You would never be able to use the rules of the game to prove that a statement is both true and false. The system would be free of internal paradox. This seems like a bare minimum requirement for any logical system. Complete means that the system would be able to answer any question you could possibly ask within its own language. For any well-formed mathematical statement, the system would be powerful enough to prove that the statement is either true or false. There would be no unknowable truths, no questions that the system was fundamentally incapable of resolving. This was the great quest, to find a single, consistent, and complete foundation for all of mathematics, to prove that the game was perfect. And into this quest, Kurt Gödel threw a logical thunderbolt. He did it with a masterpiece of mathematical reasoning, a proof of breathtaking ingenuity. He essentially figured out a way to make mathematics talk about itself. He developed a clever coding system that could translate statements about mathematics into statements within mathematics. Using this system, he was able to construct a very peculiar and self-referential mathematical sentence. The sentence, when translated back into English, said in essence, "This statement cannot be proven." Let us pause and feel the beautiful, dizzying, paradoxical nature of this sentence. Let's call this sentence G. Now let's ask the question, is G true or is G false? Let's assume for a moment that our mathematical system is consistent, which we hope it is. First, let's consider the possibility that G is false. If G is false, then its claim, "This statement cannot be proven," must be incorrect. And if that claim is incorrect, it must mean that the statement can be proven. So, if G is false, we can prove it. But if we can prove G and our system is consistent, then G must be true. This is a flat contradiction. We have proven that if G is false, then G must be true. So, this path is impossible. G cannot be false. Therefore, G must be true. Its claim, "This statement cannot be proven," must be a correct statement, which means that we have just discovered a true statement, G, that by its very nature can never be proven within the system. This is the heart of Gödel's first incompleteness theorem. It demonstrates that any mathematical system that is powerful enough to do basic arithmetic will always be incomplete. There will always be true statements within that system that are, in principle, unprovable. They are mathematical truths that are true for no reason that can be formally captured by a proof. They simply are. They are mathematical ghosts that exist outside the machinery of logic. This discovery was a profound shock to the mathematical world. It meant that the dream of a complete and final theory was shattered forever. Mathematics, the very temple of pure reason, contained within itself a fundamental and unavoidable limitation. There will always be more truths than we can ever prove. The landscape of mathematics is infinitely richer than any map we can ever draw of it. Gödel's second incompleteness theorem was in some ways even more devastating. It showed that any such consistent system can never prove its own consistency. You can't use the rules of chess to prove that the rules of chess will never lead to a contradiction. You simply have to assume it as an article of faith. This is not a statement of failure. It is a statement of profound and beautiful humility. It tells us that reason has limits. It tells us that intuition, insight, and a belief in truths that lie beyond proof will always be a part of the mathematical endeavor. The world of mathematics is not a closed, finite, perfectly knowable system. It is an open, infinite, and endlessly mysterious landscape. And no matter how far we explore, no matter how much we learn, there will always be a new horizon of unknowable truths, beckoning to us from just beyond the edge of reason. Section 10: The Language and the Listener. Our journey through the silent, elegant world of mathematics is drawing to its close. We began with the uncanny mystery of its power, the unreasonable effectiveness of a ghostly, abstract language to command the physical world. We have walked down two great, opposing paths to explain this mystery. We explored the idea that mathematics is a beautiful game of our own invention, a magnificent tool we forged to match the patterns our minds were evolved to see. And we have dared to imagine a timeless, Platonic realm, a universe of perfect mathematical truths that we do not invent but discover. We have seen a single number pi sing a universal song, and we have found another, I suppose, fiction to be a cornerstone of reality. We have stood at the very edge of reason, and have been humbled by the existence of truths that lie beyond proof. So where does this leave us? Is mathematics a human invention? Or is it a universal language? After this long and winding journey, perhaps we can begin to see that the question itself may be flawed. The choice between invention and discovery may be a false one. Perhaps the truth is not an either/or, but a both/and. Perhaps the truth is a dialogue. Imagine a beautiful, intricate seashell washed up on a beach. The shell itself, with its perfect logarithmic spiral, is a product of the universe. It was formed by the unthinking evolutionary processes of a living creature, following the physical and mathematical constraints of growth. The spiral is a discovered truth, a form that nature itself has produced. Now imagine a human being walking along this beach. They see the shell, and in their mind something miraculous happens. They perceive not just a hard object, but its beauty, its pattern, its elegance. They might be a scientist who recognizes the spiral and connects it to the Fibonacci sequence and the golden ratio. They might be an artist who is inspired to incorporate the shape into a painting. They might be a child who simply holds it to their ear and imagines they can hear the ocean. In this moment, a dialogue occurs. The language of the universe, written in the form of the shell's spiral, has found a listener. The pattern existed before the human arrived, but its meaning, its beauty, its connection to a wider world of ideas, is born in the mind of the observer. The mathematics is both discovered in the shell and invented in the layers of meaning we wrap around it. This may be the deepest truth about mathematics. The universe may indeed be written in a mathematical language. The fundamental laws, the constants like pi, the geometric forms like the spiral of a galaxy or the curve of spacetime, these may be objective, discovered truths. They are the grammar of reality, the syntax of existence, waiting patiently to be heard. They are the seashell on the beach. And our minds, forged by evolution, are the listeners. We are uniquely tuned to hear this music. Our brains are hardwired with the basic templates of number, space, and logic, the cognitive tools that allow us to perceive the patterns of the universe. But we are not just passive listeners. We are active, creative interpreters. We take the raw, discovered truths and we weave them into the beautiful, formal systems of arithmetic and geometry. We create the symbols, the axioms, the proofs. We invent the elegant language and the intricate symphonies of formal mathematics to describe the simple, powerful melodies we have heard. Mathematics, then, is a collaboration. It is a shared creation between the universe and the human mind. The universe provides the deep, silent, underlying structure. The mind provides the language, the framework, the consciousness to recognize that structure and to call it beautiful. One cannot exist without the other. A language with no one to speak it is just silent potential. A listener with nothing to hear is just empty awareness. This perspective dissolves the old paradoxes. Mathematics feels like a discovery because its fundamental truths are not of our own making. We feel the profound awe of stumbling upon a pattern in the prime numbers, or a new geometric truth, because we are touching upon a genuine feature of reality. And yet, it also feels like an invention because the formal systems, the symbols, the very culture of mathematics, is a human creation. We built the cathedral, but the laws of architectural stability and the properties of the stone were there before we began. So, as you drift into the quiet space of sleep, hold this beautiful dialogue in your mind. The universe is whispering its secrets in a language of number and form. And you, and every human who has ever lived, are the lucky ones. You are the listeners, the interpreters, the ones who can hear the music. You are a part of the conversation. And the conversation is endless, beautiful, and filled with a wonder that will never ever cease. The final answer to our question remains a gentle mystery, a space for quiet contemplation. And that is a beautiful thing. For now, let the questions fade. Let your mind rest from its long journey. Feel the simple, solid truth of your own body, the gentle, rhythmic logic of your own breath. You are a part of this elegant, mathematical universe. And tonight, you can rest in its silent, perfect order. Sleep well and dream of beautiful numbers. Good night.